Okay. So homework exercise was to try to figure out what the threshold for connectivity is. Anyone manage to prove it? No? Okay. So let's well, okay. So let's see if we at least guess it. So okay, so what's the question? So for which values of p do we expect GMP to be connected? And the hint was that it's like the calculation that we tried to do in the last class, and in the end maybe half succeeded, but easier. So So there's a common theme in the examples that we've seen so far, in the finding subgraphs and trying to find matchings, and that is that you want to try and identify the obstruction. So when we were looking for subgraphs, then maybe we had some sort of very dense bit and then some kind of sparser thing around it, and the thing you were supposed to count was not the copies of H, it was the copies of F, this dense subgraph inside. Finding a copy of F was the obstruction for finding a copy of H. Does that make sense? Right, so the most difficult thing in finding a copy of H is finding a copy of this dense bit F. F is the obstruction. Is this a word? Is that a word or not? Without the C. Like that? Okay. Is there a general rule about this? Isn't there sometimes a double C? Is there never a double C? Never. Okay. So similarly, when we were looking for a matching, then, so the obstruction is sort of the most likely thing to go wrong. The obstruction was just having a vertex of degree 0. The argument was essentially that once every vertex is degree 1, larger sets are likely to have good neighborhoods. We didn't prove it, but that's basically the idea. So let's try to identify the obstruction here. What do you think the obstruction is to a random graph being connected? Exactly. So the hope would be the obstruction might be the existence of an isolated vertex. Right? So if there exists an isolated vertex, then certainly the graph isn't connected. And what did we prove last time? So proposition what did we prove last time? About isolated vertices. We proved that if P is at most 1 minus epsilon log n over n, then there exists an isolated vertex, with high probability. Okay, so up to basically log n over n, you have essentially no chance of being connected because you're very likely to have an isolated vertex, a vertex with no neighbors. Okay. So let's try to prove that theorem maybe, if P is bigger than 1 plus epsilon log n over n, then with high probability GMP is connected. Okay, so this in this precise sense, isolated vertices are the obstruction for connectivity. We're 1 minus epsilon and 1 plus epsilon. Yeah. Epsilon is is positive and fixed. Then n tends to infinity. So really, we can prove, if we tried a little bit harder, we could prove a stronger result, giving quantitative bounds on this epsilon and really determining exactly what happens. This was done by Erdös and Rainey in one of the very first papers on random graphs. So it's a very early, very sort of basic and classical result. Okay, so how are we going to prove this? Yeah.
Why you showed the first result last class?
Yeah. Should I remind you the proof?
Yeah.
Yeah. Okay. So let's recall the proof. So proof of proposition. So what was the proof? Exactly. Chebyshev applied to X, which is the number of isolated vertices. Right. Expectation is like n to the epsilon. Variance is small because any two are basically independent. The independence is the edge between them, which probably isn't there, so it doesn't make much difference. Okay. Okay? Questions? So, we've done last class. Okay, proof of theorem. So, the question as always is, what do you want to count? Right? When you're trying to prove something about the random graph, what you should do is try and count something. You should choose the correct thing to count. Yeah, that sounds like a good idea, right? Let's count. So, at least there's idea. Okay. So this will turn not to be exactly the right thing to count, but it's a good starting point. So we're going to let's modify it when as we get there. So, okay. Why would this be a good thing to count? Why would it be a bad thing to count? Uh-huh. Yeah, exactly. Right. So x equals 1 if and only if connected. But how are you going to count the expected number of connected components? And also, how is the expectation going to tell you about x being 1? We quite like it when x equals 0 corresponds to one thing and x being positive corresponds to the other thing. So I guess we could just subtract 1. Not so crazy. But yeah, what would the expected number of connected components be? Feels difficult to It's okay, but it's still a good idea. Let's just modify it a little bit.
We count the number of paths between edges.
Ah, this is a very different idea. So, idea 1. Here's idea 2. X is the number of
The sum
Two.
of the soma dos caminhos entre cada par de vértices.
ah. Huh. So, arguments in favor and against. Why is this a good variable or bad variable? So, summing over u and v.
The length of the path.
No, the number of paths. This is what I understood. Yeah.
There's zero path, then it's gonna
Yeah, so if it's connected, then you know that between each pair there's at least one. How is the sum going to tell you that? Maybe the product, right? The product over u and v of the number of paths. So if there exists u and v which is disconnected, this product is 0, otherwise it's not. Okay. So x equals x at least 1, x or non-zero, if and only if connected. How are you going to calculate the expected value of this thing? Looks even trickier, right? Okay. Yeah, these are good ideas. Let's keep going. Right, it doesn't have to be a totally new idea. You can take one of these ideas and modify it a bit, maybe to make it easier to compute.
You can fix u there.
Uh-huh.
If you fix a vertex, if there is any path between you and every other.
Uh-huh. So x is the sum or the product over v of the number of uv paths. Is that right?
Yes.
For any fixed v. Yeah, so again, x is non-zero if and only if connected. Yeah, so good modification. Now it definitely looks easier than before. Still looks quite difficult though. This product, expectation of a product is trouble. I mean, how would you do it? I mean, you want to use linearity, so I guess maybe you could write this as a sum of indicator functions and then multiply out. But then you get some, yeah, it looks scary. More ideas? So that's a hint. So this is a nice idea, but I think this is just too difficult to compute. So I think you should focus on this idea. This was a good idea that just needs modifying a bit. You don't need to modify it very much. Just need to say it in a different way, perhaps. Sorry?
The size.
Yeah, so the size should probably come in at some point. I'll get rid of this. Yeah, so the expected number of components of a certain size will depend on the size, right? So it'll be it matters how large it is. So perhaps we should. Sorry?
The size of the largest.
Yeah, that's not a bad idea. But once again, how are you want something you can calculate the expectation of, right? You want something that's yeah, a sum of things that you have some chance of computing. So. So, I don't think that's exactly what you mean. So what exactly do you mean?
Trying to find a bipartite graph.
I think you're missing a word. I mean, it's not hard to find a bipartite graph.
But that takes every vertex.
Complete sorry.
Yes.
Yeah. So it's every edge.
Yes.
Right. So what are we really saying as in like? So if the graph is disconnected, then there must exist what? There exist at least two components. So in particular, there exists a component here, and maybe a bunch of components over here, such that what? Such that there's no edge from here to here. Right? Does it make sense? Disconnexal? Desconnexal? Disconnexal. It's okay? That was the... Yeah, okay. Sorry, that was the question. Yeah. Right? Does it make sense? Right, it says if and only if. If you're connected, this doesn't exist, because you couldn't get from left to right. If you're disconnected, you're not connected, then just take a component, and there's no edges to the rest. Right? So now what should we count? Number of those things, right? So for a particular component, then you can count that. But I want to know whether there's one of these or not. Right? This thing is now equivalent to this existing or not existing. So we should count the number of these. Right? So the number of, maybe I'll call it xk. K is here. Number of pairs, k, n minus k, with no edges in between. So if you like, k, k, n minus k, complement. Does it make sense? This is this complete bipartite graph in the complement. This is what I thought you were. Yeah. Now you should definitely say it was what you thought. Right. Okay, we'll do this for each k. So G is connected, or G and P is connected. If and only if xk equals 0 for all k equals 1 up to n over 2, I guess, right? Uh-huh, please.
Things in K are all connected.
Right, so very good question. Very good question. So to show this existed, then we took a component. So it could be like a tree or something, right? It's just some connected graph. But
Is it complete?
no. So it won't be complete.
So why is it K?
Yes. Thank you. So this is a very good question for two different reasons now. So first, this is not quite what I mean. You're quite right. So what I really mean is a k, n minus k in the complement of GMP. That's what I really mean. So as a subgraph. So you want all of the edges to be in the complement, so non-edge of GMP. So that's So that's one of the reasons it's a good question. The other reason it's a good question is because I didn't say what I was doing with these edges here. Here, I took it to be a component. And here, I completely ignored the edges inside. And that's because we didn't really need the edges here, right? We didn't need to say what was, we didn't need, so I'm not going to use the fact that this is connected. So I know basically nothing about what happens here. I know a little bit about what happens here, but I'm just going to ignore that information. So I'm saying that there exists this complete bipartite graph in the complement, and okay, whatever else. So you're right. So it's not. So there is some extra information that we could have used if we wanted to. And actually, the difficult thing about the proof last time was that we really had to use that information. That's what made it more complicated. Here, we can just ignore it. So we're lucky. OK. OK, so what we're going to do, we're going to count the expected size of xk, show that it's small, show that even when you sum over k, it's small, and that'll imply that it's probably 0, which means G is probably connected. Right? OK, so let's do that. What is the expected value of xk? Sorry, is the strategy clear? It's OK? No questions? OK, so tell me the expectation. So equal to. No, not, yeah, so right, so sorry, let me say it again. So here it was connected, but here we're just ignoring this completely. So the only condition, the thing we're counting, are these complete bipartite graphs in the complement. Yeah, so you don't need to worry about the edges inside here. So this is just a k set, which is why I'm going to make it equals. Exactly. Yeah.
And choose k
Yep.
times 1 minus b to k times n minus b.
Exactly. Is it clear? So we sum over k sets of the probability. The k set gives us one of these. Right? I guess if k equals n over 2, then there's the annoyance with double counting, but let's not worry about it. OK, so this is at most. Who remembers their bounds on these things? This is at most. I want to be a bit better than that. Do I really care? I think I care.
E times n over k
Yeah.
to the power of k.
Yeah. So yeah, so you're right that n to the k is an upper bound, and often that's enough. But here our k can be pretty big, so maybe we want this k to the k. And this guy's at most.
E
Yeah, exactly. Right. We'd like that to be small. So first thing to observe is there's a factor of k in common. It's equals en over k e to the minus p n minus k to the k. So how are we doing now?
Sum all x's, sum all the expectations.
Sorry, so first I want this to be small. So why is this small? Sorry? Yeah, we have to use the bound on p. So what do we have? This is at most en over k e to the minus 1 plus epsilon times n minus k over n times log n, so there can be an n. Right? To the k. Thank you. Are we happy? So if k is smaller than, so if this thing, there's two cases, right? If 1 plus epsilon n minus k over n is bigger than 1, then this term definitely beats that one. Right? I mean, I think we might win by a bit. Say 1 plus epsilon over 2 or something. So if k is much smaller than n, then this is true. But if k is roughly of order n, well, the worst case is this is n to the minus 1 plus epsilon. Sorry. The worst case is k is n over 2. Right? So this could be n to the minus 1 plus epsilon over 2, but you've got an n over here. Why are we nevertheless okay?
You also have over n over 2.
Yeah, exactly. We're over k, and k is in this case big, right? This case is k small, this case k is big, so this thing's only basically a constant. This is like 1 over epsilon or something. So this n to the minus 1, this thing easily beats this n over k. N over k is roughly a constant in this case, right? This is the case when k is much smaller than n. This is the case when k is order n, right? So in either case, this thing is at most n to the minus epsilon k or something over 2. Should I do that more carefully, or are you happy to check it? So if k is very small, then you win because this k doesn't matter. If k is order n, then this term is already constant, and so this wins easily because k is at most n over 2. Right? You don't have to go all the way to n. To n over 2. It's okay. And actually, you win by much more. When k is large, then you win by much more than this. Okay. So now we just sum. So what do we have? I'll put it here. So what's the argument? The probability that GMP is not connected by this observation is at most the sum from k equals 1 to n over 2 of the probability xk is at least 1. Okay? If G is not connected, then one of these things exists. Then sum xk is at least 1. and the probability that some xk is at least 1 is at most the sum of the probabilities. This is just the union bound. Or, if you like, Markov. Right? What is this sum? This sum is the expected number of xk's that are positive. Sorry, strictly positive. Perhaps I should explain that, because I used it implicitly last class, and you all stared at me as if I was crazy. So let me explain. Why is this an application of Markov? Well, let's apply Markov to y, which is the number of k such that xk is at least 1. The event that G is connected is equivalent to what? By the observation. Y is 0, exactly. Right? And so the probability that GMP is not connected equals the probability that y is at least 1, right? The same event, which is at most, by Markov, the expectation of y. But what's the expectation of y? By linearity, that's equal to the sum over k of the probability that xk is at least 1, which is this. Right? In this case, it's really just the union bound, but the union bound in this case really is just Markov. Right? I mean, so I also did the same thing implicitly the last class. This is what I meant. Okay, so this thing is at most what? They are bound here. Sum over k is 1 to n over 2 of n to the minus epsilon k over 2. Which is what? I mean, this is a geometric series or whatever. So this is at most twice n to the minus epsilon over 2. Which is 0. Right. Is it okay? Questions? So, this probability, you'll note, this sum is dominated by the term k equals 1. Right? It's much bigger than the other terms. K equals 1 corresponds to what? An isolated vertex. Right? So you can sort of already see in this proof that the obstruction to the proof, at least, is isolated vertices. Right? And this also shows up in the threshold. So yeah, I should say that something actually much stronger is true. So if you do this more carefully, then you can show that, in fact, you can see exactly where the transition happens very precisely, just by doing this calculation more carefully. But something even stronger is true. So you can see it really is given by this, these isolated vertices. But something even stronger is true. What's the stronger thing that's true? So suppose we think of GMP in a different way. Suppose instead of fixing P and choosing things randomly, we just add edges one by one at random, starting with no edges at all. Right? So start with n vertices and no edges. And then just add an edge at random. Add another edge at random. add another edge at random. Just keep going. Right? So perhaps it's not hard to believe this behaves very similarly to GMP. In fact, it's a refinement of GMP. It turns out that with high probability, the moment that this graph becomes connected, right? At some point it'll become connected, and then it's connected forever. The moment at which this graph becomes connected is exactly the moment at which the last isolated vertex disappears with high probability. Okay, so the hitting time for the event that there's no isolated vertex is with high probability the same as the hitting time of the event that you're connected. Right? This really is the obstruction in this much stronger sense. So that was only proved later, but it's also true.
Sorry.
Yeah.
Why is this not exactly GNP? Because I always thought GNP like that.
So this is in fact GNM, which is actually the random graph model that Erdős and Rainey introduced. So GNM means that you fix the number of edges to be m, and then throw the m edges in randomly. What is GMP? GMP is an averaged version of this, where first you pick m not deterministically but randomly. So if you pick m according to the binomial distribution, and then, so n choose 2p, and then throw the edges in at random, you get GMP. So GMP is sort of like it's like a smudged version of the actual Erdős-Rainey random model, so which is essentially this one. Right. So we work with GMP normally because it's easier to calculate. So GNM is more you get finer results. So if you can prove something about GNM, it's stronger than proving about GMP, but it's hard to work with. So normally, the normal thing to do is to try to work with GMP. If it doesn't have the properties you want, then sometimes you have to work in GNM. Yeah.
This resulting dot seems like the one we used sprinkling, because since you have all the vertices with an edge, you can just sprinkle a little bit more, and it's hard for two connected vertices not have another edge going to the whole graph.
Right. So the problem is, so suppose you tried to prove it like that. So you'd say, all right, first I prove that at this point you don't have isolated vertices, and then try to sprinkle to kill all the other isolated components. So I guess the problem might be is you might have something like this. And
Now it's very hard for you not to have an edge.
so you're now going to add epsilon log n over n density of edges. And there's 2n possibilities. So you expect epsilon log n. So your probability of failure is n to the minus epsilon. But if you have n to the epsilon of these things, then you're dead. So it could be, so the thing you have to worry about is what if your random graph has no isolated vertices, but more than n to the epsilon isolated edges? Then when you sprinkle some more edges, you're likely to miss one of them. Yeah, so you can probably get around that, but it's an issue. I mean, this proof is very simple, right? So why? Yeah, but that kind of idea it's a nice idea, say, for the matching problem or something. When you find you're not quite in the situation you want to be, you don't have a simple proof, these kind of tricks can really help. Yeah. Right. So I wanted to tell you. So finally, I managed to prove a sharp threshold for you. So here is a sharp threshold. Right. So let me talk a little bit about thresholds before we go any further. We'll come back to this. So first talk about thresholds, and then we'll talk about Hamilton cycles. Sorry, I'm writing this in English because I'm never happy with the translation of this. So here's a... so I'm not even sure what to write. So I understand that the standard translation of threshold is linear, which I don't like at all. I don't know what to say for sharp and coarse. So you want grosso? Grossero. Oh my God. Two S's? Like that? Thank you. Any votes for sharp? Yeah, sudden. Ingremi. I have never heard that word before. Okay. Yeah, I mean, I'm going to say sharp and coarse. So I mean, whatever. So I don't know if these things really have very nice. Okay. So it's a sharp threshold. Means that there exists PC such that if P is bigger than 1 plus epsilon times PC implies the probability tends to 1, and if P is smaller than 1 minus epsilon times PC implies the probability tends to 0. Of course, the same thing, except its P is larger than, don't even mean this. Yeah, suppose I mean this. So a coarse threshold means that as if PC, maybe I should write it in a different way. Sorry. I think that's better. Huh?
The probability goes to 1 as n.
As n tends to infinity, yeah. Sorry. So this is the So there's some event. Let's call it A, which depends on n. Right. This is always as n tends to infinity. And this is the probability of A. Right. So we say that A exhibits or has a coarse threshold or a sharp threshold if there exists a PC with these properties. Right. So, which properties have thresholds? And I mean, it's more general than this, but we can think of this thing as being a family of graphs on n vertices, if you like. So the event can be that GMP has a certain property or lies in a certain family of graphs. So which properties have thresholds? Let me tell you a theorem. So I think when you first see this definition, there's no reason to particularly think that any property has a threshold. Why would thresholds exist at all? But then in practice, when we actually tried to look at things, and we found they were everywhere, right? And this theorem of Bollobás-Thomason, which is not very difficult to prove, just it shows that there's a good reason for this, that they really are ubiquitous, so that every increasing property has a threshold, has at least a coarse threshold. And we saw already, well, I say, we haven't actually proved it, have we? We haven't proved that coarse thresholds exist, but they do, and we will prove it. Okay? So every increasing property has a threshold. Is it clear what an increasing property is? Almost certainly not. What does this mean? So the property is going to be A, not quite A. And this is going to mean that if G is a member of A you should think of as being a family of graphs on n vertices. Okay? And you should think of n tending to infinity. G is in A, and G is contained in H, implies that H is in A. Okay, so adding edges doesn't take you out of the family. So give me some examples of increasing families. Very good. The property that there's a triangle in GMP. Or in the graph. Let's try that. 2. Connected. I mean, anything that's like it has this is increasing, right? Okay, as long as it has the thing is increasing. Okay, so the examples that we've seen have this property. Yep.
A question about the definition. That PC must exist for every epsilon positive, right?
Right, so, yes, sorry, true. Sorry, there exists a PC such that this is true for all fixed epsilon. Yeah. Yeah. Okay. But here we're just going to prove a coarse threshold. Right? We're not going to be able to prove a sharp threshold.
But it's true for sharp threshold, right?
No.
Not all.
No. So an example of a property that does not have a sharp threshold is this one. Okay. And we'll prove that next week or the week after or something. Maybe even this week. I'm not sure what we're going to do. Anyway, so we'll prove that the property that there's a triangle has a coarse threshold and not a sharp threshold. But having a coarse threshold, having a threshold is a much more basic thing. So what's the proof? So you tell me the proof. Yep. Yep. Increasing. So if you have a graph that's connected and you add an edge to it, excuse me, it's still connected. Right?
It's not exactly what this said.
So you're worried that H might not be a graph on n vertices. So yeah, so I should say, and H is a graph on with the same vertex set as G. Yeah, sorry. Yeah, so this was supposed to be implicit in what I said, but you're quite right. This is, yeah, it's not formally the same thing. Yeah, so exactly. You're not allowed to say take a connected graph and then add a vertex and be like, ah, it's disconnected. Right? Yeah. 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 Okay, good. So what's the proof?
P equal 1, then the property must be satisfied.
True. Right, unless it's trivial, I guess. Yeah, so I guess non-trivial. Well, yeah, I suppose if it's trivial, if PC is 1, then this can't happen. Trivial meaning if, yeah. Maybe it's okay.
I was thinking about first going for P equal 1 and finding that the property must be satisfied, and P equals 0, it must not. And then somewhere in the middle by, I don't know.
By the 0-1 law. So this is that. I mean, this is how you prove it by in percolation or whatever, right? I mean, you have to leave at some point.
Yes.
Right. So it's true that the probability is increasing, the probability of the event. So what you want to do is you want to say, all right, here's P, here's the probability of the event A. So at 0, then this probability is 0. And at 1, it's 1. And this is an continuous increasing function. So it must look like this somehow. Why is that a threshold? What if like it's at, at 1 over n, it's got as far as a quarter, and then it gets to sort of at 1 over root n, it gets as far as a half, and then at 1 over log n, it gets as far as 3/4, and then finally gets to 1. Okay, here it's 1 over root n. So let's check the definition. So does this function that I've drawn exhibit a threshold? So this is good because the fact that no one answered it means you don't understand the definition. Right. So why does it not have a threshold?
Depends on the other ends.
So I mean, if PC is 1 over root n, it has to be that for every p that's little o 1 over root n, that it tends to 0. But here's a p. Here's a p that's 1 over n. 1 over n is much smaller than 1 over root n, but it's a quarter. Probably doesn't tend to 0. And here's a p that's much bigger, 1 over log n. But the probability is 3/4. It doesn't tend to 1. Right? So the fact that this function is continuous and increasing is not enough to give a threshold.
The shape of this should change with n.
Right. That's what we have to prove, though, right? I mean, yeah. So the theorem says exactly that this will become steeper and steeper as n gets larger. Yeah. Okay, but why? So maybe I'll start giving hints. We'll see how it goes. So let's define P epsilon to be the infimum over P such that the probability of A is at least epsilon. So I guess what I mean is probability that that GMP is in A, right? GNP is in A, is at least epsilon. Now, what we observed just now was that this probability, this is increasing it's also continuous, right? Not sure I don't think we even need it's continuous, but anyway, it's increasing. Right, so this infimum exists. And in fact, at this infimum, it equals epsilon, the probability. So, what do we want to show? What we want to show is that we go from this probability epsilon, right, this probability tending to 0 slowly, to this probability being close to 1 just by multiplying p by a large constant. What do we want? So claim there exists c, depending on epsilon, such that the probability that GMP is Gn c times p is in A is at least 1 minus epsilon. Right? So first I claim that's equivalent, or at least implies what we want.
When that event GMP is an A, is
Yeah.
that what you're calling AN over there?
Yeah, so it's a family of graphs with n vertices. Yeah, so you can think of a property as either being a family of graphs or the property of being in that family of graphs. Right? It's sort of just two ways of doing the same thing. So I'm gonna think of A here as being a family of graphs on n vertices. And it's an increasing family if it has this property. Right? That's what it is here.
Sorry, you mean is increasing in P, right?
Yes, thank you.
I know this may be a
Uh-huh.
crazy question, but there is a problem if P epsilon equals 0.
I don't think so. Sorry, if p epsilon equals 0, that means what? It means that the empty graph. Yeah, sorry. So this is right. P epsilon is a function of n as well. I hope it's clear. So if p epsilon is 0, that means that for any positive p, this probability is epsilon. But we could take p to be 1 over n to the 100. So we're very likely to have 0 edges. So therefore, the empty graph must have the property. But if the empty graph is in A, and A is increasing, that means every graph is in A. And if every graph is in A, then it trivially has a threshold at 0. So, yeah, so it's fine, but for some slightly silly reason. Yeah. More questions? So, is it clear that this claim implies the theorem? No. Aha. Right. So, what's happened? So, let's do this graph again. So, this probability has increased up to epsilon. Right? This is the probability of A. Okay? And this is our p epsilon. P epsilon. Now, what we want to do is we want to show that by the time, so this is 1, this is 1 minus epsilon, we want to know how long it takes to get here, right? And then afterwards, whatever, it goes up in some way. P1 minus epsilon. And I claim that this is at most a constant times this. So if that's true, then we can take PC to be any point in here, the point where it's a half or whatever, and then any p, which is smaller than PC over this large constant, the probability will be smaller than epsilon. And any p where it's larger than this large constant times PC, it'll be bigger than 1 minus epsilon. now just let epsilon tend to 0. This is going to be true for every epsilon. Right. Does it make sense?
Sorry, Rob.
Sounds like not. Uh-huh.
And then CP epsilon? Is G and CP epsilon there?
Thank you. Yes. Yes, thank you. Does that make sense? So PC can be anywhere in here now. And if P over PC tends to 0, yep.
Does that C, okay, it depends on epsilon, but it depends on n?
No.
No?
No, I mean, sorry. I mean, when I write this, this means that it depends exactly on the things in here.
So we are getting a stronger result than the coarse threshold.
I mean, it's equivalent, really, because, I mean, it's just it's a different way of writing. Instead of using asymptotic notation, we're using epsilons and deltas or whatever. If this is true for every epsilon, this is exactly what having a coarse threshold means. Right? So this going to 0 just says that for all epsilon, P is, so let's say 1, P is greater than C of epsilon times PC. Right. This C is going to go to infinity as epsilon goes to 0, at least in the proof. Going to 1, sorry, now. So P over PC goes to 1 implies that for all epsilon, P is greater than C of epsilon times PC. Right? Because it goes to infinity. Sorry. Yeah, thank you. Right? P over PC goes to 0, implies for every epsilon, P is less than PC over C of epsilon. Right. So the conditions tell you that you're bigger than this, and then this tells you that in fact your probability at this P is bigger than 1 minus epsilon for every epsilon. So it tends to 1. And here your probability is smaller than, I mean, okay, so it's the, okay, so at least it tells you this. It tells you you've got from here to there quickly, but it's the same thing going backwards. Right, I mean, there's only a constant factor between these things. So if you divide by this, you're smaller than P epsilon, so your probability is less than epsilon. Right? Is it okay? More questions? I'd like you to understand this. It's not, it shouldn't be too difficult, I think. It's okay? As usual, at least half the faces that I have absolutely no idea if you understand or not. Anyway, okay. Let's try and prove it. So, what's the proof? So we're going to use an idea that we used before. Sprinkling, right? I'm going to use sprinkling. So what have we got? We've got a random graph that's C times denser than the original one. Well, that contains C copies of the original one. So let's let G1 up to GC. Let's just pretend it's an integer. Who cares? and then be copies, independent copies of Gn p epsilon. And note that Gn c p epsilon contains, in the sense that, well, as I'll say in a second, the union of all of these things. Meaning, if you take this union, what's the distribution? So yeah, so perhaps I'll say it again. So instead, what is the distribution of this union? It's a random graph, right? You take C independent copies of Gn p epsilon, take their union, that's a random graph. What's its distribution? Exactly. It's just exactly, right, what's the probability of an edge here? All the edges are independent. It's just probability you included at least one of these, which is 1 minus probability you weren't included in any of them, which is that. Right? But 1 minus p to the c is at most c times p. I mean, you can expand it out. Or use the union bound, whatever. Maybe it's Markov again. Anyway. Anyway, so this thing is sort of contained in Gn c p epsilon in the sense that there's an obvious coupling that embeds this one and this one. This is just take all the edges in here and then add in some more random ones. Right? So the probability that this guy is in A is at least the probability that this guy is in A, which is at least the probability that at least one of these guys is in A. Right? Let me write that. So probability that Gn c p epsilon in A is at least the probability that of the union of the event I equals 1 up to c of Gi is in A. Why is that?
I'm sorry.
Yeah.
Is that bound correct? Because if you pick p close to 0,
Yeah.
I mean, 1 less than 0.
When if p is very close to 0, so multiply this thing out, the 1's cancel. Yeah. So the second term is small. Yeah. Yeah, in general, it's some silly inclusion exclusion.
I think it's binomial thing. You just put the c inside. Binomial.
Right. I mean, yeah. Or you could just think of, I mean, each of these is probability p. So the sum of the probabilities is c times p, but you lose some because of intersections. Yeah, so. Right. Sorry, is this clear? Why is this true? Increasing, exactly. Right? If one of these holds, then, so if Gi already has the property, then anything containing it has the property, in particular this guy does. And what's this probability? Yeah, probably if each of these things occurring is epsilon. They're all independent, so the probability that at least one of them occurs is at least 1 minus epsilon to the C. Right? Each of them is unlikely to have the property, but you have C of them. And how large is this thing? This is at most e to the minus epsilon. This is at least 1 minus e to the minus c epsilon, which is at least 1 minus epsilon if c is at least log 1 over epsilon or something. Right?
Can you repeat the sequence of inequalities?
Sure. So the first one is this coupling argument, the factor increasing. Now, what's this probability that GI is in A? Well, these guys are each independent copies of Gn p epsilon. So by definition of p epsilon, the probability that GI is in A is equal to epsilon by using continuity. Whatever. I mean, it's only at least epsilon. But anyway, it's equal to epsilon. So this probability is equal to epsilon for each of these guys, and they're all independent. So the probability that what's the probability of the union? It's equal to 1 minus the probability of the intersection of GI not in A, which is probably 1 minus epsilon, independent, so it's a product. So it's 1 minus the product over C things, 1 minus epsilon.
What probability of not being in A is 1 minus epsilon?
Probability of GI not being in A. So let me write this line properly. 1 minus the product I equals 1 to C, probability GI not in A. This is using independence and so using the definition of the GIs. Right? So this is okay?
Yeah, the equality is okay. Now the next step.
Next step. This thing has probability 1 minus epsilon.
Why?
Something like smaller than 1 minus.
I mean, so this is continuous. So in fact, so it's okay. So do I rather? So okay, let's try two different proofs. First proof. This function is continuous. Therefore, this infimum occurs at the point where it's equal to epsilon. Okay. Second proof. This is at least epsilon. This is at most 1 minus epsilon. So this is at least 1 minus this. Okay. Okay. So either way, it's fine. I suppose there's some slight annoyance that. Yeah, sorry, so if it's not continuous, if you took an infimum, maybe it was greater than or equal to epsilon down to this point, and then jumped down at this point to something much smaller. So yeah, so we don't have this at the infimum unless it's continuous. But it is continuous, so it's fine. I mean, should I prove it's continuous? Kind of obvious, right? Increase p by a tiny, tiny, tiny amount, and you didn't add any edges, so it's not going to help you, right? Was that proof clear? Increase p by 1 over n squared, and you're not going to add a single edge. So, with high probability. So your probability can't jump. Right. Is it okay after that? Yeah. So now it's. More questions?
I have another.
Yeah, please.
Why sprinkling works here? I mean, intuition.
You've got a lot of space, right? But I mean, it's a very general result. But any increasing properties, it has to have a very simple explanation. So what's it saying? I mean, so once you've got to the point where you have a chance of the event being true, then okay, you might get unlucky, it doesn't happen. But if you had another chance, then if you had lots of chances, then one chance is going to happen, right? I mean, perhaps you're asking for is there a reason why you should guess that sprinkling is a good idea in a particular situation. It's not clear there's an easy rule. I think intuition is a complicated thing, right? It's a subtle thing. You're going to build it up by seeing lots and lots of examples of things. And so after you've seen lots of examples, it becomes obvious, or it becomes natural to think of it, at least. And also, if you used it a lot, then you can see instantly if it works, right? I mean, after you've seen lots of proofs like this, then, the proof is just, someone shows you the statement, you say, I don't know what to do, they say sprinkling, you're like, oh, of course, right? And then you're done. Right? But only once you've seen it lots of times. So I think that if the question is about intuition, then yes, I agree that intuition is extremely important, but I don't think there's a magic bullet. So you just have to see lots of stuff. You expose yourself to lots and lots of proofs, and the intuition builds itself. It's good to be exposed to the correct kinds of proofs, right? The correct kinds of mathematics, the correct kinds of ideas, because then your intuition will build on those kind of ideas. Like if you see a bunch of stupid ideas, then it's gonna screw up your intuition, right? Because I think, maybe I should break into 100 different cases and analyze them one by one, and then yeah.
Would you suggest somewhere you can look up like the formal treatment of sprinkling?
Formal proof of this. So I'm sure it's in Alan Spencer. I'm not really familiar with any books. I don't really read books. But I'm sure it's treated in Alan Spencer. I'm sure it's treated in BOLLOBÁS's book on random graphs. I'm sure it's treated in, there's also a Janssen-Wuczynski book on random graphs, which I also haven't read, but it's supposed to be nice. So, any of these books on these nice books of random graphs, I'm sure they will talk about it and do it properly. With different levels of formality. So the BOLLOBÁS book does things is more formally. Maybe Alan Spencer is a bit more hand-wavy. I'm hand-wavy, right? So I don't mean it as a criticism. Right. Let me tell you. Okay, sorry. So I was going to tell you something else about thresholds. So every increasing property has a threshold. So which increasing properties have sharp thresholds? Most of them, few of them. How common is it? Turns out, somewhat surprisingly, that basically all increasing properties have sharp thresholds, with the exception of the one we saw last week, the inclusion of a small subgraph so the family of things that contain h for some h, for some small fixed h. This was proved by Erhard Friegut in about 20 years ago, and it's an extremely beautiful, extremely good result, an extremely beautiful proof. Too difficult for us to give, but it basically says that if a property does not have a sharp threshold, there must be some sort of local obstruction. So the property basically looks like, in some slightly complicated but precise sense, it looks like the event G contains H for some H, for some fixed H, or slowly growing H, to be more precise. Right.
So
Yeah.
it allows for the family to grow also to modify.
Sorry, in all of these, then n is increasing, and as n increases, the family changes.
The connected properties like that.
Yes, right, exactly. So really, you're looking at one for each n. But you can, you can restate all these things in these epsilon delta form, right? So you don't have to think about, maybe for odd numbers it's connected, for even numbers it's containing a triangle. So then, what's the threshold? It keeps jumping back and forth. Right, you just restate it in this form, and that problem goes away. We just state things correctly. Right. So yes, you should think of this as being a bit like a 0-1 law. For those of you who know 0-1 laws from probability or from, I guess, ergodic theory or whatever, there'll be lots of places that they appear. It's sort of saying that, right, that the probability has to be very close to 0 or very close to 1, except in a very narrow range, as long as your property is sufficiently global. Right? If it's very local, then it might not be, but if it's sufficiently global, then which is, I guess, perhaps the analog of translation invariant or whatever properties you need for 0-1 laws in other areas. If you don't know 0-1 laws, don't worry about it. It's not a... But. Okay. So... So here's another very sort of sparse object you could look for in a random graph or in a graph in general. So a Hamilton cycle is just a cycle that goes through all of the vertices. Okay? Definition. And it's a cycle, not a walk, so it can only pass through each vertex once. Right? So you're not allowed to do, it's not an Eulerian tour, if you know what those are. So you're not allowed to do something like this. Right? This is forbidden. Okay? It has to be, there's a cycle. Okay? This is okay, this is not okay. Just to make sure we know what we're talking about. Okay? Okay, so question. What conditions guarantee that there's a Hamiltonian cycle in your graph? Yeah, so that's definitely necessary, right? So exists, well, Hamilton cycle implies that the min degree of G is at least 2. This way? What's a counterexample? There's one. Yeah, it's got min degree 2, so there's a min degree 2, and there's no Hamilton cycle. Right, yeah. It must be bipartite. So here's a counterexample to that.
Yeah, it's bipartite. I don't know what I'm saying.
Okay.
Maybe no degree 4.
Minimum degree 4.
No vertex with degree 4.
No vertex with degree 4.
No.
You're trying to get rid of that example. So yeah, so it's an increasing property, so we're going to need some increasing condition. So things like, how many edges guarantee that you can find a Hamilton cycle? Right? That's the kind of question that we normally ask. So how many, what's the number of edges of G is at least some M implies exists a Hamilton cycle. So for what M is this true? So okay, n choose 2 works, right? If you have at least n choose 2 edges, then you have lots of them. So give me a graph with many edges and no Hamilton cycle. Yeah, very good. Almost the best construction. Can you beat it? Yeah. Right. Okay, so you can like almost all the edges without having a Hamilton cycle. And this is actually the best. So exercise, this is best. Okay, so this is it's a nice exercise. Try and prove this.
So what do we need to prove?
That this is the graph with most edges and no Hamilton cycle. So this maximizes the number of edges. Okay, so this is not quite the right condition. Right, number of edges, you need way too many. You need basically almost all of them, all but about n of them. So okay, let's try and look for a more useful condition. So in particular here, we didn't have min degree 2, right? So I'm going to suggest an alternative measure of the density of the graph that might give us a Hamilton cycle. So, I mean, we might guess, what about number of edges and min degree at least 2? But that's also silly because you could do something like this, right? I mean, there's no... So how about, I mean, the first suggestion was min degree 2, that didn't work. What about larger min degree? What min degree is sufficient? Min degree of G is at least what implies exists Hamilton cycle. Okay, give me a construction.
I'm thinking about induction.
Less than n over 2.
Yeah,
2 clicks.
very good. There we go. 2 cliques. So you definitely need at least n over 2. So, theorem, Dirac. Not sure what decade, sorry, long time ago. This is correct. So min degree at least, min degree of G strictly greater than n over 2 implies there exists a Hamiltonian cycle. This is not the famous physicist Dirac. This is his son. I think that's correct. Okay, how to prove this? Maybe I'll get rid of this. Okay, seems like a reasonable idea. On n, presumably. So, how are you going to do it?
You take off vertex,
Uh-huh.
then you have the cycle.
Right, so okay, so here's your G, and there's some vertex, and it's got more than n over 2 edges. And then here's your G prime, and there's some Hamiltonian cycle going all the way around it.
And then it has true consecutive because it has more than now.
Seems like a pretty good proof. What's wrong with it? Who can spot the error?
Maybe the condition doesn't hold on G prime.
Aha. There we go. We didn't check that G prime has this minimum degree. Right? Is it true that del G prime is strictly bigger than n minus 1 over 2? Right, yeah, so we might have lost, if something was right at the borderline, it lost a neighbour, then it might have gone down by 1, not a half. Okay, so that was a nice idea, but it didn't quite work. And right, this is it's a real problem. How are you going to apply induction? You have to find a subgraph with the correct min degree. It's not very clear how to do that. Or even if one exists. It's not very small. Does there exist a vertex that you can remove that doesn't have any neighbour that's right at the boundary? Not sure. I mean, for example, what if you took this guy and added 2 edges to it? Then if you remove one of these vertices, then you kill your Hamilton cycle. Okay, but maybe you should remove one of the others.
Start with the vertex and somehow show that you can always find some neighbor that hasn't been visited. So
Sorry, you want to just kind of walk greedily. Good idea. Yeah, that's a nice idea. So idea 2, totally different idea. So just greedily walk. Dong, 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 dong. I'm stuck. So why are you stuck?
Every edge goes back.
Yeah, exactly. Every edge from here has to go in. And similarly, every edge here has to go in. Otherwise, you can carry it the other way. So now what?
One of those edges are the same.
Yeah, so you know you have more than n over 2 here, and more than n over 2 here, and fewer than n vertices in between. So if you like, you can find a common neighbour. Does that help?
Then you erase one of these edges and use the new one. Okay.
If you could continue on the neighbors of that theorem, the neighbor.
Some other neighbours? Or these two?
Yes.
Okay.
You can continue if you could, like, jump and then go back.
I see. So you want to do, right, this, 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 and this. And then hope that these guys have neighbours outside. If they don't, then if the neighbours inside, yeah. But yeah, you're getting close. This is a good idea. You need to change what you did a little bit. Exactly. So instead of using pigeonhole to find them with the same neighbor, let's find this vertex x, such as this guy is attached to x, and this guy is attached to x plus 1. And now we have a cycle. Why is a cycle good? Why is a cycle useful?
Any edges that,
Yeah.
any vertex that have two edges, you can go for it.
Yeah, exactly. If there's any of these vertices have a neighbor outside, now you have a longer path. Right? And then you continue. So now you've found a longer path, and just keep going. Or if you like, take the longest path that you had. So what does it say? It says that take the longest path in the graph. This says it's not longest unless it's all the vertices, but there you found a cycle. Right. So, I mean, there are various ways to do this. I think the one that I like best is that we can go from a path of length k. Let me say this has k vertices. We can go either to a path of length k plus 1 or to a cycle of length k. We can always go from a cycle of length k to a path of length k plus 1 if k is less than n. Right? This is or. Why is that? Why can you always go from a cycle of length k to a path of k plus 1?
If k is smaller than half, you choose
Mm-hmm.
some graph and it has somewhere inside.
Yeah.
If the opposite, you get somewhere outside and it has the opposite.
Yeah, that works. Another way of saying, so that's completely fine. Here's a second proof. I mean, basically the same. So I want to show the graph is connected. So if this cycle has no edges going out of it, and there are vertices left over, then the graph is disconnected. But I claim the graph is connected. Why is it connected? Well, let's prove something stronger. Let's prove every pair of vertices either have a path of length 1 between them, if they're connected, or if they're not, they have a path of length 2 between them. Why? Because he's got n over 2 edges, neighbors. He's got n over 2 neighbors. So there's a neighbor in common. Okay. So in fact, this graph has diameter, so maximum distance between vertices, 2. So it's connected, so this doesn't happen. It's probably more complicated than your proof, but it has this nice side effect. Yeah.
I have a question.
Mm-hmm.
Why can't you go from a path of length k to a cycle of length k? I mean, it exists in all.
Yeah. Sorry, I didn't check this carefully. Quite right. So, the existence of x. So, this guy has degree bigger than n over 2. This guy has degree bigger than n over 2. And there are k, which is less than n vertices. Sorry, less than or equal to n. Now. So you tell me, why does there exist such an x? Do you know?
Tem metade para cada né? Só que não pode ser metade, tem que ser maior. Então você tem que pegar de cada.
Yeah, I mean, yeah, you're just proving the pigeonhole principle. Yeah, okay, yeah, it's pigeonhole. But we have to, I mean, let's do it slightly carefully. So what do we want? We're looking for a pair of edges of the form, let's call this u and this v, of the form u x plus 1 vx. So this is, what do we call it? Ax. Now, if you look at the union of AX over all right, so what do I want to count? So there are k vertices here. Do I want to start x at this point? Well, if x equals u, then this edge is already present. I'm just asking if the edge uv is present. So first, let's observe that if the edge uv is present, we're happy. Let's assume that uv is not an edge of the graph. Okay, now we can do x from 1 up to k minus 2. And I claim that we've covered all of the edges from u and v to these guys.
K minus 3, because x plus 1 would be v.
Thank you. Yes. What? Yeah, quite right. Thank you. Is what is the set of u, w, vw, such that, what am I saying? From w between, so u goes to, I'm not including this one, but I am including the next one. And I'm including all the way to k minus 2, union vw, and w is between 1 and k minus 3. That's right. So that's 2 lots of k minus 3. That makes it disjoint, right? It covers all of these edges. And you know that you've got at least n over 2 coming out of u, including this one, which is not counted, and at least n over 2 coming out of this one's not counted. So n plus 1 over 2, they have a degree at least n plus 1 over 2, take away this one, and minus 1 over 2 times 2. If n minus 1 edges, I claim you have to have 2 from the same class. Which you do because there's only k minus 3 classes, which is at most n minus 3. So in fact, I've gained slightly. So maybe I could do it greater than or equal to here. Looks like it. I always forget. Yeah, the degrees here are n over 2 minus 1, right? So I think maybe prove that. Yeah. I mean, I don't want to think about it so much. I mean, yeah, maybe it's greater than or equal to. It looks like it. Right, so the n minus 2 edges to fit into these pigeonholes, there's only n minus 3 pigeonholes. So one of them must contain both, which is what we wanted. Right? OK. That might well be on an exam at some point. So if I'd remembered to teach it to you before today, then I would have put it on the exam this week. But now I've said it doesn't count. So maybe it'll be on the final. So final thing I want to say. I was hoping to finish early, but I failed. So what's the threshold for finding a Hamilton cycle in a random graph? So what can you tell me about it? Right, so you might guess from this, maybe it's a half, right? That certainly if p is bigger than a half, then you'll have this property by probability, so you'll be done. So it's at most a half. It's at most, well, half plus a low 1 by Dirac. Any other upper or lower bounds?
What is it implying directly?
Sorry, so there's an extra step. So if p is bigger than a half, say it's a half plus epsilon, then I claim with high probability GMP satisfies this property, has min degree at least n over 2. Because it's the typical degree of a vertex is n over 2 plus epsilon n, and it's sufficiently concentrated by Chernoff or something that is, yeah, so sorry, it's not trivial, but there's also not the bound I want, so. Any lower bounds? Yeah, right, so we already proved that you need log n over n to have no isolated vertex, right? So at least log n over n. Any other suggestions? Sorry, so we can beat the isolated vertex a little bit by using this observation, right? I don't know if that gains you just a constant in front of the log n. Or even does it even gain that? Sorry, not even that. Yeah. It gains you a tiny bit. So note also that this is harder to find than the perfect matching, right? Because at least when n is even, a Hamilton cycle contains a perfect matching. In fact, it's made of 2 perfect matchings. So we shouldn't expect this problem to be easy, and it's not. And I won't prove this, but the theorem which I think is due to BOLLOBÁS, is that the hitting time for containing a Hamilton cycle equals the hitting time for having min degree 2. Okay. So in the random graph process, so this is GM is after I've added m edges independently, randomly each time. So the minimum m such that min degree of GM is at least 2 equals the minimum m such that GM has a Hamilton cycle with high probability. And this also has a sharp threshold at something like log n over n. Okay, so this is not at all easy to prove. Even proving weaker bounds is not easy. So I think it was first proved by Posia. So this is called, I erased it. This proof of Dirac's then we saw, this trick is called Posia rotation extension. And this is useful when you're trying to prove this. Anyway, so I'm not going to say anything else about this. I just wanted to let you know that these kinds of things exist, and they can be proved by, I mean, this is even like 30 years old or something, or maybe more. This is not such a new theorem, but by modern techniques. And so it's even true, so this is a paper that I saw just the other day, that at the moment at which the Hamilton cycle is born, so this minimum m, not only do you have one Hamilton cycle, but you have many, but moreover, even if at each vertex you delete slightly fewer than half the edges in any way you like, you still have a Hamilton cycle. Okay, so it's very sort of robustly Hamiltonian, this graph, even at this very early stage. And the reason is that this vertex has degree 1. While it has degree 1, all of the rest of the graph is getting very dense. Right? It's getting lots and lots of edges, the average degree like log n or something. It's just this last few guys, these holdouts, they're waiting for. And when they're finally there, then you just won. Right? You have so many Hamilton cycles that you can do essentially whatever you like. This is the reason it's true. It doesn't make it easy to prove. But at least perhaps, if you think about it, it's not as surprising as it seems at first sight. Right, so let's stop there. The exam is on Friday, right? We all agreed? Okay, so it'll be during class. And you all you've all seen Volner and had done you know how to do all the problems on the Lista, right? Hopefully. Okay.
How many hours?
Sorry?
How many hours?
Just during class, just 2 hours.